You are listening to Science Coast with Mallory Havens.
And Chris White.
And
Joe Kozminski,
Chair of Physics Department here at Lewis University.
Lepton's rule.
Again, physicists.
Welcome back, Joe.
Thanks. Good to be back.
In a continuation of our conversation about sustainability, energy, we're going to talk about fission and whether fission is a reasonable alternative to burning fossil fuels at this particular point. And it's not necessarily sustainable because there is only so much uranium fuel that exists on the surface of the planet. And just like with coal and oil and natural gas, when we use up all the uranium, it will be gone. But it can be potentially a source of energy which doesn't create carbon, contribute carbon dioxide to the atmosphere. So as we shift towards a more sustainable energy portfolio, is fission, our nuclear reactors, a reasonable solution in the interim short-term time period? And there's a couple of different ways of thinking about it. Yes, if we quickly ramp up the number of fission reactors in the world, we can generate a lot of electricity, which could potentially decrease the amount of coal and natural gas that we burn to generate electricity. But there are negative consequences. Everybody remembers what happened at Fukushima, as well as what happened at Chernobyl in the Ukraine. And we don't want that happening in our backyard.
Island.
To a much smaller extent, yes.
But I'm just saying there's more.
That's true. One faculty member when I was a grad student used to describe it this way: with the typical methods by which we generate electricity, the pollution that's generated is uniformly distributed across the planet into the atmosphere and into the waters. Whereas with reactors, nuclear reactors, you can concentrate that the pollution that's generated as a waste of the process into a single place. And then you can try to, maintain control of that waste and secure it so that it doesn't get out into the wider world. So with that, I'm going to pass it off to Joe Kozminski, and he's going to explain to us how this whole thing works to begin with.
Yeah, so nuclear reactors take advantage of the radioactivity of uranium. So uranium is an unstable element, and it will split apart. And in doing so, it creates some other lighter elements, and also gives off a particle called neutrons, which are part of atomic nuclei. And if you put a bunch of uranium together and you have these neutrons coming off, you can induce more uranium reactions. This generates a lot of heat, and that heat can be used to convert water to steam and use kind of traditional steam generators that you would see in a fossil fuel-fired power plant.
But isn't that also how they make atomic weapons?
It is. So there are control systems, control rods within nuclear reactors, such that you only get one neutron out for every reaction. These control rods capture the other neutrons. So we don't let it go, just kind of balloon and cause that explosion.
Except when we don't, like Chernobyl.
Well, that wasn't a nuclear explosion, but anyway.
It was a meltdown.
It was a meltdown.
It was an explosion that blew the top off the reactor facility and distributed all of this concentrated radioactive pollution over a wider area and into the environment. Mm-hmm. So that was a breach of containment.
Right.
And that was a very poor reactor design, and those are not found in any reactors in the United States and have been decommissioned around the world for the most part, I think.
What happened at Fukushima? I know a tidal wave, but how did that...
Yeah, so the tidal wave hit the reactor facility. It was right on the coast. It was a tsunami, so very powerful wave. And essentially, it flooded two of the reactors, shut down some of the emergency systems, some of the emergency generators, and so that was certainly, but it could have been prevented. That there were reports 10 to 15 years in advance saying that this could happen, and it was kind of a roll of the dice to say, well, it probably won't happen, so we're not going to build the protections.
You mentioned the word meltdown. Meltdown implies that something gets super, super hot. And even if a nuclear reactor is quote unquote shut off, where they shoot the control rods back down so that the fission ends, you can still have a meltdown. And that's actually what happened at Fukushima. So they were successfully able to shut down the reactions. However, the byproducts that had been created before the tsunami are still there, and they're still radioactive, and they're still decaying. So there is still energy being released in the reactor core. Mm-hmm. The big challenge with these accidents is that you have to continually cool the reactor core, even after the control rods are pushed in, and the fission reactions cease. The need to continuously cool by circulating water through it is ever present. And in fact, this is one of the concerns that's happening right now in the Ukraine at the Zaporizhzhia reactor facility. And people are very concerned that even though they're not operating the reactor cores to generate electricity, the reactor cores still need to be cooled. They still need to have electricity from outside coming into the facility to make sure that the reactor cores don't get too hot from the radioactive decay of the fuel, which would then potentially cause it to melt.
Does the water become radioactive?
It can collect radioactive isotopes, and if there is enough neutron irradiation, some of the hydrogen atoms in the water can become tritium isotopes, which is radioactive.
Do they just recycle the same water over and over?
Yes. In the modern systems, they do that.
In the old systems, they just put it in a pond out back?
Sometimes they would do that, yes. But they don't do that anymore. And you may, for people who are familiar with tritium, you may hear in the news about tritium releases from various places that get into the groundwater, and that's basically what happened.
And that's how people get superpowers?
Actually, that is true.
Yeah.
That is true. And if you get exposed to tritium, then you become immortal. No, that's not true.
People are going to be breaking into nuclear power plants.
Do not drink the tritiated water.
That's actually good advice. I shouldn't ever be allowed to give advice on the air. So what are your perspectives, Dr. Kozminski?
I think nuclear energy actually has great potential as a very clean source of energy. There's no carbon dioxide produced in the reactions. And nuclear energy could provide a very stable base load for the other renewables. So when the sun isn't shining, the wind isn't blowing, nuclear energy can provide that very constant amount of energy that we always need.
I am uncomfortable with nuclear energy just because of the waste problem and the accident problem. I don't trust people to not screw up. We have notoriously, throughout the history of humankind, repeatedly screwed up. So I think that it's great that it's not contributing to carbon, but you do have all this waste. What do we do with it?
Yeah, and human factors have actually been played a big role in the three disasters that have been discussed here. But in terms of the waste, there are ways to contain it. There's a waste repository in I think it's the Carlsbad Caverns in New Mexico. But there are also technologies out there for reprocessing waste, and other countries do this in Europe and Asia. It's been illegal to reprocess waste because we haven't had nuclear policy changes in the United States since the 1970s. Really until about October 2022, when we have started to provide some money for developing these reprocessing technologies. So a way to kind of recycle some of the nuclear waste.
Reprocess it into what?
So not all of the nuclear fuel can be used. Only a small percentage is U-235, uranium-235, which is the nuclear fuel that generates our nuclear energy. So there's still U-235 left in that fuel source, so we can extract that as well as some of the plutonium byproducts.
Do you do that through centrifugation? Because I know that to enrich the uranium, you have to have massive centrifuges.
That would be one way to do it.
Okay, I solved it.
So where does the plutonium come from?
That comes from the decay chain of uranium. When the neutron goes into uranium 238, actually, not 235, it produces plutonium nucleus.
So most of the uranium on the planet is the U-238 isotope.
Yes.
And a tiny fraction of it is the U-235 isotope.
Correct.
And the U-235 isotope is what we split, or what splits to generate the electricity.
Yes.
But the U-238, in the process of being around when the U-235 is breaking apart, can absorb neutrons and turn into plutonium, which we can then extract and then use that as fuel.
That's correct. Yeah, it becomes fissile then.
So we're actually generating fuel in the process of burning fuel.
Yes.
Do they have to replace the uranium in nuclear power plants?
They do every few years, depending on the size of the nuclear power plant. They have to go in, they have to extract the old fuel, put it into a containment system, and then replace it with new nuclear fuel.
How do they do that? Like, obviously people aren't walking in there. Robots?
Essentially, large cranes and things are used. And then you're using concrete and water for containment.
Water turns out to be a pretty good absorber of the radioactive products that are, or the radiation that's coming off. So it's a lot of beta and gammas. So water works fairly well in absorbing those. Yeah. And neutrons. Water is a very good absorber for neutrons.
Yeah. I just, I'm not a physicist, and I've seen the HBO special.
It's not too
for
late.
Chernobyl. Okay. I'm more likely to become an aviation mechanic than a physicist.
Oh, cool.
So what do you do with the waste that is the waste problem only because we're not recycling, or is there still going to be waste that's radioactive that we can't recycle?
There would still be radioactive waste that we would have to deal with even after the reprocessing, but it would be reduced. And there are also advanced reactor technologies that could be used to burn some of that nuclear fuel and create much shorter-lived radioactive waste.
Because isn't the half-life of uranium something like 1 billion years or something to that effect?
Yeah, but if the half-life is 1 billion years, I don't worry about it too much because the probability of a particular atom decaying at any particular moment is so small. You could take U-238, and in fact, they use it for military applications, and you could carry around some U-238 with you, and it would have very little impact on you. It's when you split the U-235 into smaller pieces, those smaller pieces have very short, by comparison, half-lives. Some of them on the scale of less than a second, and others up to minutes, years, hours, years, decades. So that the challenge is to take the waste and put it in a secure location for about 50 or 100 years, while many of the isotopes decay away.
That's a lot better than waiting 1 billion years to get lead.
Exactly. But the challenge is, even after 100 years, you still have some residual radioactivity for the isotopes that have half-lives that are measured, in hundreds or thousands of years. Right. So it's never going to be the type of thing that you can dig back up and then say, oh, look, this is great. We can use this for something else. You're going to want to keep it stored away for basically until humans don't exist anymore, which is one of the challenges. And one of the things I always thought was funny is, well, why don't we just shoot it at the sun? But it turns out that there's too many rockets that blow up on launch.
That just happened.
So, if you wanted to take this waste and basically send it to the moon or send it to the sun, it's actually much more complicated than you might imagine. And there's too many risks associated with that. And so
Plus the aliens would get mad.
That's true. That actually is true.
They're like, you can destroy your own planet. Don't destroy your solar system.
Yes. So right now the basic idea is that you take all this stuff, concentrate it, and then put it into these caverns. That you dig out these caverns in these salt mines that geologically should be stable for thousands, if not millions of years, and then just leave it there.
What happens if there's a big earthquake?
Well, it's geologically stable. They pick places that aren't on faults.
Yeah, but we had an earthquake in Illinois,
but not to the scale. So you have these very large, salt structures, and even if there was an earthquake, the salt structure is not going to disintegrate. But hopefully, what I would think you want to do is put it in a location which is going down into the mantle of the Earth, so that the Earth just absorbs it.
Oh, yeah, because the center of the Earth is radioactive.
Which is why the center of the Earth is actually molten. The heat we talked at the very beginning, maybe it was a previous episode. The heat of the Earth is not going to go away anytime soon, and it's because of the radioactivity that exists in the core of the Earth.
Yeah, just drill that far down. We've got that, right? No problem.
They tried.
My understanding as a child is you could just dig a hole to China.
They tried.
I tried that in my mom's garden and it didn't work.
Yeah, no. Your shovel didn't cut it?
No, it didn't cut it.
Doesn't work.
It's because you got so deep that it started melting. Right?
And I got in trouble.
Yeah. All right. The views, thoughts, and opinions expressed are the speaker's own and do not represent the views, thoughts, and opinions of Lewis University. The material and information presented here is for general information purposes only. The Lewis University name and all forms and abbreviations are the property of its owner, and its use does not imply endorsement of or opposition to any specific organization, product, or service. This podcast was produced in the WLRA podcast studios at Lewis University. Visit lewisu.edu for more information about Lewis University. This is Science Coast with Mallory Havens.
And Chris White.
And
Joe Kozminski.
thanks.
See you later.